So the secant method is this. It's a really big formula. And I'll try to draw you a picture of what the heck we are doing when we use the secant method. So what happens in the secant method is that we have to choose two initial iterates, not just one. We've got to choose two of them. So maybe I choose this to be my initial x0 value. And then I evaluate the function here so I can tell the point the function is at. And then I've got to choose another initial iterate, call it x1. And I find the value of the function there at x1. And then this is where my drawing is not really going to do it justice because I can't draw perfectly straight lines. But ideally, we would create a straight line between this point and that point and follow it all the way down to the 0, right? So pretend that blue line is completely straight. And then this is going to be the next iterate. And then between x1 and x2, I'm going to evaluate the function here at x2, find that point, and then I'll have to draw a straight line between this point at x2 and this point at x1, and I know that's not straight. Sorry. And then this point where that straight line intersects the x-axis is where we're approximating the 0 of my function to be. That will be the third iterate. And then we'll evaluate the function here at the third iterate. And then what we continue to do is we use the last two iterates to draw a perfectly straight line between those points on the function. And then we look where the line crosses through the x-axis. And then that point of intersection, the x-intercept for the line, is the next iterate. And so this is called the secant method because each one of these lines that we're drawing are called secant lines. The blue line that goes from this point at x0 to this point at x1, that's called the secant line. And we look for where the secant line has an x-intercept, generate a new iterate, and then we create another secant line between this point and that point, and wherever the secant line has an x-intercept, that's where we generate our next iterate. So we're over and over again producing a new secant line, a better secant line, a closer secant line that gets us closer and closer to the iterate. And so this looks a little bit crazy, but you can probably understand this a little bit better if you really think way back to Calculus 1. And think too about last time we met when we had Newton's method. In Newton's method, your new iterate was your previous iterate minus the value of your function there at the previous iterate divided by the derivative of your function at the previous iterate. And the idea behind the secant method is that we like the Newton's method. It worked really nicely, except what if we don't want to take derivatives, right? Maybe there's some legitimate reason why you can't take the derivative of a function. And if you can't take the derivative of a function, you only know the function itself, then you might be forced into using something like secant method. And instead of dividing by the instantaneous rate of change, does that bring back memories? In Calculus 1, sometimes you call the derivative the instantaneous rate of change. We're just going to divide by the average rate of change, And dividing is the same thing as multiplying by the reciprocal, and you should hopefully recognize this part right here, as being the reciprocal of the average rate of change for this function. And so the average rate of change between the n-1 iterate and the n-2 iterate would be this. So if I multiply by the reciprocal, it's the same thing as dividing by the average rate of change. And so this is like an approximation to Newton's method. This is saying I can't really do Newton's method because for some reason I can't take a derivative. But even without taking a derivative, I can still get an approximation to Newton's method. And this is what we call the secant method. Any questions? Okay. You could also kind of derive the secant method formula by, drawing this picture here and trying to figure out how to calculate where x2 is going to end up. Right? Forget about all the green and think just for a minute about the blue stuff. Right? If I want to know what is the slope of this line, the slope of the line is rise over run. And so that would be like f of x0 minus f of x1 divided by x0 minus x1. And the slope-intercept form for a line would be like y minus y1 equals m times x minus x1. That's my slope-intercept form of a line. And then the y value I might want to work with is, let's say, f of x1. This is my big M value. And the x value I'm trying to find is this. I want to find a point where y is equal to 0. So let me change the y into a 0. Okay, now we can rearrange this equation a little bit. Distribute the m. And then solve for x2. M x1 minus f of x1 equals mx2. And then divide everything by m. And we get x2 equals x1 minus f of x1 over m. And once again, m is the average rate of change that we're dividing by. So anyways, my point is you can derive this secant method formula kind of by drawing a picture like this, draw a secant line, figure out where the secant line is going to intersect, and then you eventually get back to here. But it's important that you know the secant method formula and you can use it. So let's use the secant method, and on your test, you'll be allowed to use the TI-30X2S calculator to calculate square root 2 within 0.1. And it tells me what initial iterates to use. I think I said this before, but on a test, I'm also going to tell you exactly what initial iterates to use. That way I can grade it more easily. And so let's find out. Here's k, here's xk, here is, what else do I need? F of xk. And then we would need to calculate f of xk minus f of xk minus 1 divided by xk minus xk minus 1. Okay. Right? And then I have to take the formula, right? Let's say this is m. My secant method formula would be xk plus 1 is equal to xk minus f of xk divided by m. I know that looks different, but hopefully you see that's equivalent. I think I shifted the index by 1 maybe. All right, and so when k is equal to 0, xk is equal to 3. When k is equal to 1, xk is equal to 4. Oh, and we haven't even talked about what function yet we're trying to solve a 0 for. We're trying to find the 0 of what function. If I want to calculate the square root of 2, and we've done this before, right? We do x squared is equal to 2, so x squared minus 2 is equal to 0. The function that we're trying to talk about here, I'm trying to find a 0 of the function x squared minus 2. If I can find a 0 of this function, then I've calculated the square root of 2. So what is f of 3? That'd be 3 squared minus 2. Seven. And then what is f of 4? 14. Now, we'll have 14 minus 7 in the numerator, which is 7. 7 divided by 1 is 7. And then to get this next x2 value, it looks like we're going to need x1, which is 4, minus 14 divided by 7. 4 minus 2. Did I do all of that right? Gotta double check my work here. I'm looking at this formula when I take my next iterate. So I'm looking at 4 minus 14 divided by 7. So I think it's 4 minus 2. All right, what is f of 2? 2. Yeah, 2 squared minus 2 is 2. And then I need to take 2 minus 14, which is negative 12, divided by 2 minus 4, which is negative 2. So I get 6 for that average slope part. And so when k is equal to 3, x3 must be equal to 2 minus 2 over 6. That's 2 minus a third. So it's like 5/3. (1.667-ish). And this is the point where you need to actually start picking up your calculator, right? Because I don't know what 5/3 squared is. 25 over 9. I don't know. Then subtract 2. And then you keep on going like this. It might take 1 or 2 more iterations to get in between like 1.3 and 1.5-ish. But that's how you do it. Are there any questions about how to do this? Do you feel like you could do this on your test? You can remember the formula. You can make a little table. You can produce these iterates.
If I memorize the formula, yeah, probably. We'll find out Monday.
Yeah. Okay. And
I have a question.
yes.
How do you see if it's in point 1 on this
Oh, maybe I'll tell you this on the test, but the square root of 2 is around 1.41-ish. In fact, I don't even need to tell you this because you could have a calculator, right? You could actually type in square root of 2 on your calculator and see what the square root of 2 should be.
Okay.
Yeah. And then make sure you're within 0.1 of that. Okay, so I'll move on as long as y'all feel good. If you are wondering about anything, raise your hand, ask me a question. Let's do this again. I'm going to make the same kind of table with my iteration number, my iterate, the function evaluated at that iterate, and then this idea of like an average slope, which is this. And then, to get the next one, the next iterate, it's going to have to be this iterate minus my function divided by that average rate of change, the average slope for my secant line. And once again, we have the same two starting iterates. We've got 3 and 4 already picked out for us. And this is one where I wish I had a calculator. I see an iPad. That's not my iPad though, so I probably can't unlock it. I've got a phone calculator. Oh, except I need the arctangent. I don't know if my phone does that. I'm just going to have to make you guys do it. I see a few calculators out there. What is arctangent of 3?
Or
1.25. Let's round to like 4 sig figs.
1.24905.
2490.
05, yeah.
Okay, so there's 4 sig figs. That'll be good enough, I think. What is arctangent of 4?
1.326.
Okay. Now, do this. Take open parentheses 1.326 minus 1.249, close parentheses, divided by 1. Well, I guess you don't need to divide by 1, right? But what's the difference between these two?
.077.
0.077?
Like,
Okay. Let's give me 4 sig figs. Give me 2 more digits.
that's all.
Oh, yeah, you're right. Sorry. My bad. I forgot we had already rounded there. Okay. So that's good. And then next I need 4 minus 1.326 divided by 0.077. What is that going to be?
Negative 13.221.
Negative 13.22. What is arctangent of negative 13.22?
Negative 1.495.
Now tell me, what is open parentheses negative 1.495 minus 1.326 close parentheses divided by open parentheses negative 13.22 minus 4 close parentheses.
I got 0.163 or 1.64.
1.64?
0.164.
Oh, 0.164.
Yes.
Okay, then over here, we need the previous iterate, which is negative 13.22 minus negative 1.495 divided by 0.164. What is that?
Negative 4.104.
Negative 4.104?
Yeah. 04.
Okay. I just remembered I can use Excel to do this too. So let's try that. And maybe this goes by a little bit quicker. Let's see. So here's my iterates. 0, 1, 2, 3, 4, 5, and so on. The x values we're starting with are 3 and 4. My function is the arctangent function. So there's my arctangent. And then the slope is going to be the next, open parentheses, the next one minus the current one divided by, and shoot, I should start on this one, make it the previous one minus, no, the current one minus the previous one divided by the current iterate minus the previous iterate. That rise over run thing, average rate of change. And then to get the next iterate, we take the previous iterate minus the function value divided by the average rate of change. And so that is my secant method. Let's see what we get. Okay, we were right so far, because we got something like negative 13.27. We got something like negative 4.12 something. There was round off error because we were only keeping so many sig figs. But that's what we got for the first 3 iterations. And this would have taken a while, but what I wanted to show you is if we were to keep using the secant method, it doesn't converge, right? Look at column B. These are where my iterates are. The number just keeps getting larger. I mean, it bounces around, I guess. 70, 30, 3,000, 1,600, and then big number, big number, big number, big number. It's diverging. A lot like Newton's method sometimes failed, right? You remember when Newton's method diverged away for the same function? We were trying to find arctangent of 0 equals 0. But for the arctangent function, Newton's method tended to diverge away if we didn't start close enough to 0. And since the secant method is just kind of like an approximation of Newton's method, it's going to do the same thing. It will also fail. Now, I couldn't find any ways to make the secant method enter a cycle. Remember how Newton's method would enter a cycle and it would just bounce back between like 0, 1, 0, 1, 0, 1? That's pretty easy to find for Newton's method. But I sat down and tried to make the secant method go through a cycle. But first of all, the secant method can't be in a 2 cycle, right? Like it can't just bounce back and forth between 2 numbers. Because the secant method draws a secant line between those 2 numbers, and it would never choose one of those 2 numbers unless it was 0. And if one of those 2 numbers was a 0 of the function, then you've already solved your problem. I tried to make the secant method go into a 3 cycle, and I worked through the algebra with pencil and paper and found out that that was not possible. The secant method can never enter a 3 cycle where it bounces back and forth between 3 numbers. So I disproved that. But what I don't know is maybe the secant method could enter a cycle with 4 numbers or 5 numbers where it bounces back and forth between 5 different numbers over and over and over again. That's yet to be proved or disproved as far as I know. That could be a really good topic of like undergraduate research. If you want to do like an undergraduate math research project, you could think about that problem for a little bit. How do you make the secant method enter a cycle of 4 or more numbers? Or alternatively, how do you prove that it could never enter a cycle of 4 or more numbers? Maybe some of these already done it, but if they have, I don't know.
Brown University said that it does enter a cycle at times.
It does? Oh, cool. Is there an example on their website?
X times the exponential of negative x squared.
Interesting. Okay. I'll have to take a look at that later. Did it say how long the cycle was? Was it like a 4 cycle? No? Okay. Anyways. Next, we're going to implement the secant method in Python using a for loop. And then we're going to use this code to do the same calculation. But it's nice to know how to use Python. So we'll boot that up. You guys don't know this, but Google and ChatGPT have really ruined everything because you used to be able to just like wonder about a question, you know, and like be bored for a minute and think about it. And now ChatGPT is right there to tell you that Brown's already figured it out. That's okay. So we want to implement the secant method using Python and using a for loop. And so what I'm going to do this time, I think, is actually say, no, I'm not going to do that. Right now I'm telling it my initial iterates, and then I say 4k in range 10. We'll do 10 iterations. What will we do? First of all, I should define my function. As we'll do x squared minus 2. And then my loop, my for loop is going to say x sub k is going to be equal to x sub k minus 1 minus f of x sub k minus 1 times, I'm just going to say divide by m. Because I don't want that line of code to get super long and nasty. Instead, I'm just going to call a new variable m and define it as f of x sub k minus 1 minus f of x sub k minus 2 divided by, and I forgot my parentheses, so I got to go back and put my parentheses in, divided by open parentheses x sub k minus 1 minus x sub k minus 2. And then I've calculated my new iterate. And after I get my brand new iterate, what do I do? Let me change this up a little bit. Because maybe what I want the first thing my loop to do is this. Yep, that's what I want. Okay, and then at the end we say print the newest iterate x sub k.
Shouldn't we change the variables at the end?
You could. I think it would work either way, whether you want to do it at the start or at the end. Let's give it a try and see if we get something. Oh, so you see my issue? I'm used to Microsoft Excel where you use the little caret for the exponent, but you actually use 2 asterisks for the exponent in Python. Let's try it again. There we go. So at least this works. This is a way to implement the secant method where it works. I'm sure there's others, and maybe you can find ways to improve this, but I guess that does the trick. Okay, do you have any questions about this? How it works? One thing you can do in Python, and I'm going to create a new sheet for this to show you, is one thing you can do is I could have said, let's make x equal to numpy dot zeros and give it like 10 entries in an array. And then I could have told it that the first entry in the array was going to be 3, and the second entry in the array was going to be 4. And then what I could do is just have f of x k minus f of x k minus 1, and make this x k minus x k minus 1. And then that's how I would calculate what happened. X k plus 1. And we'll see what happens if I do this. Oop. So I'm going to change that loop. Ran out of bounds a little bit. Okay. So what happens when I do this? Oh, I know what I should do. Well, it's not super obvious to me what I need to do. But our first 2 iterates were 3 and 4. That's what we specified, 3 and 4. The reason it kind of replaced the 4 with 2/3, it overwrote over the 4, is because when I say for k in range 9, k starts out as 0. And so it's going to replace x with x of 0 plus 1. So it's going to be the 1 index, and it's going to end up writing over that. But it still does the job. It still follows into the square root of 2. And this way, the way I've saved x as an array, you can see what each of the iterates looks like as it's kind of narrowing in on square root of 2 over time. And so that's nice. The reason I typically wouldn't want to do this is because this only works if I specify how long the array is to begin with, I have to allocate space and memory for that array. And I guess you could just choose like a really giant number, you know. But what I want to do eventually is, instead of implementing this with a for loop, use a while loop. And we'll talk about error tolerance here in a sec. Okay, so we did that. We implemented the secant method in Python with a for loop. The next step, like I said, is using a while loop. And suppose I want 6 significant figures of accuracy. So same exact thing. This time, get rid of the for loop and replace it with a while loop. And that while loop is going to look like while my estimated relative error is greater than some tolerance. And I've got to decide what my tolerance is going to be. My tolerance should be 0.5 times 10 to the power negative number of significant figures. And my number of significant figures that I want is 6. And then I have to get this started by making my estimated relative error greater than my tolerance. Otherwise, the loop isn't going to start. And then I say, okay, while the estimated relative error is greater than the tolerance, do this. And then how do I calculate my estimated relative error? I'm going to take my x sub k minus x sub k minus 1 and divide by x sub k. And then I need to take the absolute value of everything. Right? Okay, does that part make sense? And this way the code only does as many iterations as it needs to do in order to reach a desired level of tolerance. I don't have to guess and accidentally guess too low on my number of iterations, and then it doesn't reach a particular error tolerance. I don't have to guess too high and waste computer resources. So what do you think? Was there an easier way to do this? Was there a better way to do this? Probably. What are you thinking?
Oh, I have no idea.
Maybe C++, maybe, not Python.
C++ is easier?
Well, maybe it's not easier, like, period, but as far as do while loops for, like, the control structure.
Okay. I don't know anything about C++ or computer science at all. I'm very much, only the basics kind of guy when it comes to this stuff. So I'm sure the computer science people in here could definitely figure out ways to do this better. And honestly, Python is not a super efficient language. This is a good, in my opinion, teaching language because it's got a nice development environment. I can hit the little green play button and it interprets my code. I don't have to compile anything, blah, blah, blah. I think it's nice for teaching. But just in practice, if you actually want to do anything with scientific computing, you probably would need to learn something like C++ or even just C, because it's a less abstracted code. It compiles into a more efficient way and it runs faster on supercomputers. You would never use Python for like a large scale scientific computing thing. It's more of just a teaching tool. It's a teaching tool, and I mean it's useful for small problems, and small problems do pop up in industry from time to time. It's not completely useless, but if you had a really large math problem, then yeah, you would want to use C. Count the number of flops required to perform each iteration, then count the number of flops required to perform the calculation in exercise 5. So each iteration has quite a few flops. And of course, it depends on what function we're doing, right? But it's got at least 1, 2, 3, 4, 5. So we'll say this. It's 5 flops plus 2 more if you want to calculate the relative error, or the estimated relative error. And then how many times do I have to call my function? 1, 2, 3. And really, I guess I could have gotten away with only calling my function one time. Or sorry. Yeah. Yeah, there is actually a much smarter way I could have written this code. The way I wrote it, on every iteration, it calls the function 3 times, 1, 2, 3. And so what if the function itself requires a whole bunch of flops to figure out the function, you know? That wouldn't be a very efficient way of writing this. But what I could do is make it call the function only one time per iteration. And in order to do that, I would have to calculate this value and save it as a variable and just use that variable here and here. And then I would also need to save that into another variable so that the next loop keeps that number as the f of x sub k minus 2. But I could have written this code so that it only calls the function one time. Let's do that really quick. And that would look like f of x sub k minus 1. So I'm just creating a variable that grabs that function value. And then before I overwrite the previous thing that was storing, I need to put it in a different variable. This has to start off as something. So I've got to put this outside the loop. And then I could, like I said, get rid of all of these function calls with variables. And that's a way you could reduce the number of flops. And again, it should work, yeah, with just only calling the function one time per iteration. So plus 1 function call. And depending on how many flops your function requires, you know, that could be a lot. So not bad. There's a little bit more flops going on here than Newton's method. But Newton's method then again also requires you to evaluate the derivative. You know, every iteration of Newton's method makes you calculate the value of the function and the value of its derivative. And so if the function or if its derivative take a lot of flops, then the Newton's method falls behind here. So again, if I ask you, discuss the stability of the secant method, it can fail. It's not guaranteed to be stable because it can diverge to infinity in certain cases, like the arctangent problem. Pros and cons. So let's compare it so far with the method, the other methods we've learned, Newton's method, bisection method, and so on. We might be concerned about the stability. We might be concerned about, do I need a derivative? We might be concerned about, is it fast? We might be concerned about, do I need an initial bracket? And we had bisection, Newton, and now secant method so far. The bisection method was guaranteed to work as long as you started it out right with an initial bracket, then it was going to work. On the flip side, do I need an initial bracket? Yeah, with the bisection method, you do need an initial bracket. So that is kind of a strike against the bisection method because that's not always a guarantee. Do I need to calculate the derivative? You only need to calculate the derivative if you're dealing with Newton's method. And so that's kind of a strike against Newton's method. And then, is it fast? Well, Newton's method is fast. Bisection method is considered pretty slow. And then the secant method is considered somewhere in the middle. We are going to be a little bit more rigorous about the idea of fast and slow methods in about 2 weeks. In 2 weeks, we'll introduce things like rate of convergence and order of convergence. But for right now, what you need to know is that if your method was going to converge and you weren't concerned about the other considerations, the Newton's method is the fastest. Secant method does all right for itself, but it's not as fast as Newton's method. And the bisection method is slow